طيب. بسم الله الرحمن الرحيم. السلام عليكم ورحمة الله وبركاته. Welcome to EE21. So today's lecture will be the 21st. And in today's lecture, we're going to start talking about chapter 8, the chapter before the last one. So we're reaching the end of this course, and we're reaching the most interesting things in this course. But before that, a few announcements. Reminder that the midterm is tomorrow at 7 p.m. So I don't think this needs to be stated. So it's going to be physical, inshallah. So homework 3 also will be posted, inshallah, this week. So you'll have 1 week to work on that homework. And the quiz 4 will be, inshallah, on Wednesday. The coverage will be chapter 7, but basically 7.1 to 7.6. Okay. Just going over what we did last time. If you remember, we had a situation where we have a circuit with a resistor and a capacitor, or resistor and an inductor. So if we are to find any quantity here, the voltage or the current passing through the inductor or the capacitor, we see that we will end up with something similar to this, a differential equation of this form. X can be the value of the current or the value of the voltage, or the current or the voltage. K is actually the initial, or K is actually the it's related to the existence of the source, of an external source. Okay, we said, well, in all cases, we consider step and natural response, but there is a general form of the solution, and this form of the solution is given by this equation. So if you're looking, for example, for the voltage, what it says here that the voltage is equal to the final value of the voltage plus the initial minus the final, scaled by a decaying exponential, and this decaying exponential is centered at the switching time, in this case T0. And we saw that if we have a capacitor, and we are concerned about its voltage, then T0 or T dagger should be equal to T0. So the voltage across the capacitor cannot change instantaneously. If we have an inductor and we're concerned about the current passing through the inductor, we see that T0 equals to, or T0 dagger equals to T0. And in this case, because the current cannot change instantaneously, the current passing through an inductor cannot change instantaneously. Otherwise, T0 dagger equal to T0 plus, which is immediately after we open or close the switch. Okay, any question about the general concepts in chapter 7? Okay, seems very clear, inshallah. So now, chapter 8 is kind of like extension to what we did in chapter 7. So if you remember in chapter 7, we had, if you remember what we did in chapter 7, we had a situation where we have a resistor and an inductor, a situation where I have another situation where I have a resistor and a capacitor. But we've never had a situation where we have a resistor, inductor, and a capacitor. So in this chapter, chapter 8, we're going to consider what happens when we have these three components. Basically, we're going to be there are two possible ways of creating there's two possible ways of kind of like generating this combination. It could be in parallel, meaning that you have a resistor, an inductor, and a capacitor, and these three elements are parallel. And this is the first case that we're going to cover inshallah in today's and next lecture. The other thing is when they are all in series. So if they are in parallel, they share the same voltage. If they are in series, they must share the same current. So this is deferred to maybe in 2 lectures where we're going to talk about this situation. But let's start with what happens when you have parallel RLC circuit. We have a resistor in parallel with the capacitor and it's parallel with the inductor. Will we be getting the same form of the solution? It turns out the answer is no. It's kind of like somehow similar, but there come kind of like a very neat, very nice behavior. As a matter of fact, this situation, having a resistor and a capacitor and an inductor, is more realistic than having just a resistor and an inductor or a resistor and capacitor. Because this is naturally occurs when we have, for example, a printed circuit board. If you have a printed circuit, you have specific integrated circuit, an IC. And this IC has some lead associated with it. So this is where you connect this IC to the external elements in the circuit. Below that, usually you have a kind of like another metal, something called the ground. So if you take a side view, you see that this is your RC. Then there's some, of course, there's some insulators here, and there's some metal here. This metal is called the ground. This is insulator. So what happens here is, in this case, we have the connection with the other elements has some sort of like resistance and inductance associated with it. The fact that you have metal here, and you have metal here, and there is an insulator between them, this kind of like resembles a capacitor. So this is kind of like a very common, very general way of or this is the most common case in practice. You have a combination of resistor, capacitor, and inductor. So let's study what happens if we have an RLC circuit. Okay, so what was the key quantity that, or the key equation that we started with? We started with, and everything else depends on that. Hadi?
By using KCL, we find an equation and then use the differential to derive it.
Yes, exactly. So we ended up with having a differential equation that kind of like governs the system behavior or governs the circuit behavior. So what we want to do in this case, even in this case, we need to derive a differential equation that governs the circuit behavior. Once we derived a differential equation that governs the circuit behavior, then since this course doesn't require a differential equation course before it, we're gonna have like standard way of solving this problem. So let's try to derive the differential equation that governs the circuit behavior. So starting with the following circuit, we have a capacitor in parallel with the inductor, in parallel with the resistor. So what we need to do is let's start with applying KCL. At the upper node. So if we apply KCL at the upper node, we see that all the currents are leaving that node. So IC, the current passing through the capacitor, plus IL, the current passing through the inductor, plus IR, the current passing through the resistor, must be equals to 0. So what's the current passing through the inductor? It's C dV. So here we have one quantity that's common among all of them, which is the voltage. So let's represent the currents in terms of the voltage. So the currents are different, but the voltage across each element is exactly the same because they are connected in parallel. So this is the current passing through the capacitor. The inductor, if you want to find the current and you're given the voltage, so you need to integrate. Let's assume that the starting point is 0 here. The voltage across the resistor by Ohm's law. So this one is I. Okay, so what can we say about this equation? Well, this equation contains derivative, the function, it's a derivative, and it's integral. So it's not straightforward to simplify it, to solve it, because there is a mixture between differentiation and integration. So let's actually write it in terms of let's actually rewrite it in terms of only differential operators. So what should we do here? We need to differentiate both sides. So to get so what's the derivative of 0? 0. Okay. If we differentiate both sides, so the first term is already the first derivative. So if you differentiate it once, one more, you will get a second derivative. So it's going to be C dV squared by dt squared plus, if you differentiate the integral, you will get the function itself. If you differentiate the constant, you will get a 0, which is I. Then in this case, you will have 1 over R dV by dt equals to 0. Mohammed?
No, I just want to make sure that we differentiate the voltage with respect to time.
Yes, that's what we did. So we differentiate the voltage with respect to time. Because here, you want to find the common quantity among all these three elements, which is the voltage. So the voltage, if you know the voltage across these elements, you can find the current passing through the resistor, you can find the current passing through the inductor, you can find the current passing through the capacitor. Okay, so this is not the standard way of, this is not the standard form of solving differential equations. Usually we want to have the highest derivative, the coefficient of the highest derivative is 0. So in order to do that, we need to divide both sides. When I say both sides, because this one is 0, so you need to, if you divide it by 0, you end up with 0 by C. So if you divide it 1 over LC. Oh, sorry. Okay, this is we derived the differential equation that governs the system, or that governs the circuit behavior. So now what should we do? We should actually find the solution of this differential equation. So it turns out, so just bear with me. What you have here is a function plus its first derivative plus its second plus its the function plus its first derivative plus its second derivative somehow scaled equals to 0, which means that it requires that the function and at least its first two derivatives are of the same form. So the multiple functions that have this kind of ability, one of which is actually an exponent. So if you have an exponent, e to the power a of t, then the first derivative will also have, it will have like a scalar multiplied by e to the power a of t, the second derivative, the third derivative, etc. So if you assume that the solution is of the following form, or maybe let me write it this way, not the solution, a solution. Okay, I'm assuming that the solution has the following form. A is a constant multiplied by an exponent, and the exponent has a scale by s. So what is A here? A constant, and this constant depends on the initial condition. Meaning that what was the value of the voltage, what was the value of the voltage and the value of the current at t equals to 0, for example. S here is the root of the characteristic polynomial. Or characteristic equation. That's why when you take EE and when you take Math 208, I believe you are following the new curriculum, you will see that this problem is called initial value problem. Okay. So now we guess the solution. We assume that the solution is something like this. So now what's the next logical step here? What do you think, Shabab? Mohammed?
To find the first and second derivative of the assuming solution.
Yes, we need to do something like this. Ibrahim?
Maybe we should try it in an example.
Not really. Before that, Abdelkarim?
Try to find the constant.
Yes, we need to try to find the constant A and S, or the expressions for the constant A and S. Because A and S here, they do not, we do not have access to them. If I give you this circuit, if I tell you C equals to 0.5 microfarad, L equals to 1 millihenry, R equals to 200 ohms, and ask you to find A and S. Can you find them? No, you cannot. At this stage, you cannot. So we need to actually relate A and S to the circuit elements that we have and the initial values that we have. The voltage, the initial voltage across the capacitor, and the initial current passing through the inductor. So in order to do that, what do we need to do? We need to, we need to substitute this solution back into the differential equation. And when we substitute the solution back into the differential equation, we want to find the value of A, or the values of A and S, such that this differential equation is satisfied. So if you remember, the solution is A multiplied by e to the power st. So if you substitute it into 1, you need to take the first derivative and the second derivative of that. So the first derivative of a to the power st is simply s a e to the power st. The second derivative is you take the first derivative multiplied by s. So each time you take a derivative, you multiply it by s. So here we have a. For the second one, we have a constant, which is 1 over RC, so it will stay as it is. Then we're taking the first derivative, so it's going to be S multiplied by A to the power A multiplied by E to the power ST. And the last one is actually, we're not taking derivatives, so we're substituting there. So this is basically what we did. And if we take A to the power st, then we'll get s squared plus s divided by rc plus 1 over lc equals to 0. So we have two options. Either a to the power est equals to 0, which is in this case, it means that our solution is the trivial solution, meaning that the voltage is 0. This is not, we're not looking for a trivial solution. We're looking for a non-trivial solution. So what we need to do, we need to make sure that the other term, this one, is equal to 0. Is it clear, Shabab? Are you following me? Any question? Yes. Okay, very good. So this equation, or this polynomial, is called the characteristic Okay. So in order to make sure that this one is 0, we need to find the roots of this characteristic polynomial. And since it's the second, it's a second order polynomial, so it means that we need two. It must have two roots, whether these roots are real, imaginary, or it's actually one root with multiplicity of two. So what's the expression of the roots of this polynomial? Ziad?
We can use the general form.
Yes. S is minus b plus or minus b squared minus 4ac divided by 2a. So in this case, a is 1, b is 1 over rc, and c here, remember here, there's c that comes from the general form, and there is a capacitance, is 1 over LC. So if we simplify it, we'll get the first root is minus 1 over 2 RC plus the second root is then simply the negated version of this one. Okay. If you have two independent solution for any equation, then the solution could be any combination of these two solutions. So the total solution B of t will be A1 so sometimes we write S1 minus alpha plus alpha square minus omega naught square. S2 is minus alpha minus, so this is for simplicity. So in this case, alpha is 1 over 2 RC, omega naught is 1 over square root of LC. And this one is called the Nipper frequency. The unit is radians per second. Omega naught is 1 over square root of LC, and this case is called the resonance frequency, or the resonant radian frequency. You will see why we call it radian, inshallah, in the next chapter. And the unit is radians per second. S1 and S2 are called the complex frequencies. Any questions you have? Okay, so let me just summarize what we did. So we started with the following circuit, and we said, well, let's do this. Let's use the same approach that we did in chapter 7. Let's derive the differential equation that governs the circuit behavior. And we said that if we apply KCL at the upper node, we will get an equation that, in terms of the voltage, which is common among all three elements, and that equation has a mixture of differentiation and integration. So if we differentiate both sides, we will make sure that it's only in terms of differentiation, and this is the differential equation that governs the system behavior, or the circuit behavior. And we said, well, one possible solution for this one, and actually the solution that we are kind of like interested in, is something on the form of a to the power es of t. In this case, a is a constant that depends on the initial values of the current and the voltage, the initial value of the voltage across the capacitor, and the initial value of the current passing through the inductor. S is something called the roots of the characteristic polynomial, or the characteristic equation. Now, in order to find S, we saw that we need to take the solution, substitute it back into the differential equation, and then get back to, and then find the condition under which this differential equation is satisfied. And we saw that S, there are two possible values of S. One is S equals to minus alpha plus alpha square minus omega naught square. The other one is the minus alpha minus omega minus alpha square minus omega naught. And alpha is 1 over 2c, omega naught is 1 over c. So as you can see here, S, the value of the roots, depends on the circuit elements. So once you know the circuit elements, you can easily find the roots. Still, we haven't figured out a way to calculate A, and inshallah we'll come to it later in this lecture. But let's deep dive into some of the details here. So as you recall, the roots are S1 and S2, and they are given by alpha minus omega d. Omega d is simply like, I took this expression and write it as omega d. So if I substitute the solution, I will get a to the power minus alpha t minus or plus this term. So this term is always, alpha is always greater than 0. What happens if alpha is less than 0? You will have an exponent with the positive power, which means that things are going to grow. This is not physical. So alpha is restricted to be greater than 0, to greater than 0. this. Now, what about omega d? Omega d, it turns out, can take any of three values, or any of there are three possibilities for omega d. The first one is omega d is real and positive. In this case, alpha, remember, omega d is in this case, alpha is greater than omega naught, or alpha square is greater than omega naught. This is a response is called overdamped. And the voltage response will decay. Actually, this is not quick. This is called overdamped. The other option is omega d is 0, which means alpha equals to omega naught. And this case, the response is called critically damped, and the voltage will decay. Actually, it's the opposite. This one is quicker than the other. The third option is alpha is less than omega naught. In this case, you will have square root of negative sign. If you have square root of negative number, then in this case you have an imaginary component. This imaginary component is responsible for some oscillations. You will see that the system or the voltage will decay eventually because of the factor alpha, e to the power negative alpha t, but it will somehow oscillate before it decays. We'll talk about it, inshallah, later. But any questions, Shabab? Any question? So let's summarize. The natural response, again, which we're considering the natural response, even though we did not state it because we don't have a source, is given by this formula, and there are three components here. The first one is S1. There are four components. The first one is S1. The second one is S2. Third one A1, A2. And we can see here that S1 and S2 are called the characteristic roots, which depend on alpha and omega naught. Alpha is 1/2 RC. Omega naught is 1/square root of C. And depending on the ratio between alpha and omega naught, we can have either overdamped, critically damped, or underdamped response. Okay. Let's try to solve this exercise. So we're given this circuit, and we're asked to find the roots of the characteristic equation that governs the transient behavior of the voltage. So we have R equals to 200 ohm, L is 50 millihenry, and C is 0.2 microfarad. So what are the roots of this characteristic polynomial? Walid?
Yes, Dr. First, I think we should we find alpha first.
Yes.
And omega square naught.
Okay. Yes. Exactly.
Yeah.
So the roots. This is S1. S2 is So alpha is 1 over 2 RC, and in this case,
It's 1 over 400 multiplied by 0.2.
yes, 0.2, which is in this case 1.25. So now we found alpha and omega naught. So this one will be two, five. And this is going to give me minus S2 will be minus 12. Okay, now I found alpha. Now I found the S1 and S2. So let's see. Will the response be overdamped, underdamped, or critically damped? Let's see. Yasser.
Yes, you're gonna subtract alpha squared minus omega naught squared, and it gives us a positive answer, so it is overdamped.
Yes, exactly. So alpha squared is greater than omega squared. So in this case, we have over damped response. Also, S1 and S2 are real and non-zero. So real means they're not underdamped. Non-zero means they are not critically damped. Okay. Now, what happens if I change the resistance? Instead of being 200 ohm, it's going to be 312.5. What do you think will happen? Abdul Karim?
Alpha would be smaller.
Alpha will be larger, actually. It used to be 400.
Oh yeah, it will be larger. 200. Yes, it will be larger.
لا alpha will be smaller. Yes, you're right. Okay, so alpha squared will be 64 times 10 to the power 6, or 0.64 times 10 to the power 8 radians squared per second squared. This one is radians squared per second. Ahmed Hamid? Ahmed?
No, I wasn't.
So what is omega naught square? Will it change? Ahmed Hamid.
Omega not, no, because it depends on L and C.
Exactly. So omega naught won't change. So in this case, we have S1 equals to minus 8,000 So the other root is the conjugate of this one, the complex conjugate. So it's going to be radian per second. Remember here, J is square root of -1. So in this case, we have, in electrical engineering, we have, because the complex number is represented with J. This is not to confuse it with the I, which represents the current. So in math, you used to have I, which represents that the number is complex, but in electrical engineering, we use J to differentiate it from the current. Hadi, question?
Just I wanted to point out for the first part, alpha 2 multiplied by 400 should be 200, right?
Oh, okay, yes, okay, yes.
And for S2, it should be negative 20,000.
S2 for the first one?
Yes.
Yes, I don't know why. Okay, hold on a second. This should be 20,000. No, 13 plus 7, yeah, it should be 20,000. Anyhow, this question is in the book, so you can double check the numbers. Thank you, Hadi. Ahmed, Abdullah Al-Jireem, Abdullah, question?
Participation.
طيب, what's the response of this one? Is it overdamped, underdamped, critically damped? So remember, we classify the problem into three types: overdamped, critically damped, and underdamped.
It's overdamped.
It's actually underdamped because omega d is complex. Okay, so okay. Ahmed, question? Ahmed Al-Nafi?
Doctor, when I see omega is complex, I will write underdamped.
Yes.
Nothing.
طيب. Okay, the last part is asking us what value of R causes the response to be critically damped. So in order to solve this problem, you need to Yasser, what's the best way to approach this problem?
Since critically damped should like we should have an equation where alpha squared equal to omega squared. So we can substitute 1 over 2 RC squared and equate it by 1 over LC.
Exactly. So this means that if alpha of R is actually greater than 250, the response will be underdamped. If R is less than 250, the response will be overdamped. If R equals to 250, the response is actually critically damped. Okay, any questions, Shabab, before we start? New thing here. So when was the last time you heard about damping factors, etc.? When was the last time? Did you hear about it in Physics 101?
No, I don't remember that. I have never heard of it before.
Okay. Did you hear about, did you study the spring and mass problem?
Yes.
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 So the response of this one is like the overall response is similar to the spring mass problem. So if you recall, the reason I want to present this one is not actually part of the things that you're going to be tested on, but it's always good to have, because in most of the engineering and science problems, you kind of like take a problem that's well understood, well studied, in a specific field, which is in this case is classical physics, and you try to implement it into another field, because there are some similarities between them. There's some system similarity between them, or there's some equation, some similarity in terms of equation. So if you recall, we have the following. Differential equation. Again, I'm not going to put it in the standard for an obvious reason that will be clear in a minute. In the spring mass problem, you usually have something like this. This is a mass, and there's a spring here, and you're trying to move the spring. displace the spring along the x-axis. So from Newton's second law, we have the total force is actually equals to the mass multiplied by the acceleration, which is the second derivative of the displacement. So if we draw the what we call the free body diagram, we see that in order to move this one, you need to apply a force to the right. This is the external force. There is a friction that's slowing this force that's moving in this direction. There is a spring constant that's bringing the spring into its equilibrium state. So K is called okay. Some factor, and this one is related to the friction. So if you have frictionless surface, then gamma will be 0. So if we assume that there is no external force, this is similar to the case where we have a step, where we have a natural response. So the response is there is no applied force. So what happens here? All of a sudden the spring has, I mean, you are stretching the spring, and all of a sudden you leave the spring, and you wait for the spring until it reaches its equilibrium state. So in this case, you will have acceleration, then the friction or the damping factor is related to the speed, then you have K, and this is a differential equation that governs that system. So look into the similarity between this equation and equation 1. So if you compare them, you see that C is actually the mass, can somehow related to the number of charges. Because remember, C is Q divided by V. So if you have more charges, C would be accumulated through the capacitor plates. You will have larger C. Gamma is the friction, which is somehow related to dissipation. Or the conductance. K is the spring constant. And it's analogous to 1 over N. So you see that the similarity between them. So think about it this way. So what happens if you have spring and you have a mass? So it was initially stretched, then you leave it. So what you want from this spring is to reach its equilibrium as fast as possible. So if you have critically damped, then it will, once you leave it, it will reach its equilibrium very quickly. If you have overdamped, it will reach its equilibrium, but it's going to reach it slowly. It means that you're stretching the spring, then you leave it. So if it's critically damped, it will stay like this. If it's over damped, you're stretching it, then you leave it, so it's going to be something like this. Then it's reached, but it's slow down. If it's critically, if it's under damped, then it will oscillate somehow and then stop. This is similar to the voltage that you have. So you have a source, and that source connects to the capacitor and the inductor. Then you remove the source. If it's critically damped, then the moment you remove the source, it's usually there's no charges accumulated. So the voltage will be 0 immediately or quickly. If you have a critically damped, if you have underdamped, if you have critically damped, the voltage will reach 0 immediately. If you have an overdamped, the voltage will reduce and it will reach 0. But if you have something like it will reduce slowly, then it will reach 0. If you have something that's actually underdamped, what happens is the voltage will reach 0, then be 1, 0, 0.5, 0, 0.25, 0, 0.125, so on and so forth until eventually it reaches 0. But it's kind of like fluctuates. And this is exactly what we're doing. Is it clear, Shabab? Ziad?
If it oscillates, why doesn't it change polarity and just stops at 0 where it's equilibrium?
It changed polarity, so it's going to be negative.
Oh, okay.
-1, -2. But I'm using some sort of like hypothetical situation, but it's actually changes polarity. So if it's 0, then it's going to be negative and positive, negative and positive, negative and positive until it reaches 0. Any other question? Why we care about this one? Ideally, what you want is actually you want something critically damped. So you turn off the switch, it's closed. Overdamped is kind of like it's acceptable, but underdamped sometimes is not acceptable because sometimes it's going to affect your hardware. So that's why if you have sensitive hardware, if you have like a setup with sensitive hardware, so they don't tell you to if you deal with some very expensive equipment, they don't. If you want to turn off the power, they tell you to do it in a sequential manner. So first turn off this one, then turn off that one, then turn off that one. The reason for that, there might be some oscillation here that's going to destroy some of other things in the other part of your circuit. Okay. Any questions, Shabab? That's why this topic is interesting. It's not very hard to solve problems on it because it has a very systematic way, but it has some very interesting, very real-time applications. Okay, so let's start with the overdub response. So far what we did not talk about how to find A1 and A2, how to find the coefficients. We discussed how to find the roots S1 and S2, and we said that we can find them from the initial from the circuit elements, but we did not discuss how to find A1 and A2. Let's try to find A2, A1, and A2. So let's start with the first case, which is overdub response. So the general solution will have the following four. A1 multiplied by S1T, A2 multiplied by S2T. And remember, in this case, A1 and A2, they are actually negative. I'm sorry, S1 and S2, they are actually less than 0. Why? Because alpha is positive, so we're taking the negative side. Then you subtract it by something that's less than alpha, which means that it's stay negative. Okay. Now, in order to find A1 and A2, the first thing you need to do is you need to actually take this one and evaluate it at 0. If you evaluate it at 0, you'll get A1 plus A2. This is going to give you the first equation that you have. So you need another equation. In order to do that, you need to differentiate the solution with respect to time. We take dV by dt, then in this case you will get S1 A1 e to the power S1t plus S2 A2 a to the power S2t. And to equate it to 0, if we equate it to 0, we will get S1A1 plus S2A2. Okay, this is the second equation. So you have two equations, two unknowns. You can easily solve for them. This one and this two, you can find them from the circuit elements. So what is dV by dt? What is V here? V here is the same as the voltage across the capacitor. So the voltage across the capacitor is simply, or the current across the capacitor is given by CdV by dt. So dV by dt is the capacitor current divided by the capacitance. So that's why we have this one. So how to find the current passing through the capacitor? Usually you're not given, in terms of the initial conditions, you will be given the initial current passing through the inductor. You will be given the voltage across the capacitor. From that, you can find the current by applying KCL here. IC is simply IL minus IR. So what is IL? So what is IL here? As the initial current for the inductor. And remember, the current passing through the inductor cannot change instantaneously. So IL is simply the initial current passing through the inductor. What's the initial current of the resistor? Is simply by Ohm's law, the voltage across the capacitor, which cannot change instantaneously, divided by R. So this is going to give you the initial current passing through the capacitor immediately after the switch being opened. So, Abdulkareem?
Yes, doctor. Why is it IL minus IR?
Minus IR.
Isn't the current going? Oh, the current going from the voltage source. Oh, okay, sorry, I got it.
So it's minus IL. Thank you.
Yes, I got it. Thank you.
Okay. So in order to find the solution for overdamped, first of all, you need to verify that the response is overdamped. Because you will see in a moment, or not in next lecture, you will see that if you have a critically damped or underdamped, you will have different forms of the solution. So the first step that you need to do is you need to verify that the response is overdamped. If you verify this, then you need to find the roots of polynomial S1 and S2, you can find them immediately from the circuit elements. Then you need to find the initial value of the capacitor's voltage and the initial value of the capacitor's current. Once you found them, then you can find the coefficients A1 and A2 by applying these two equations. So once you find the coefficients, you find the roots of the polynomial, you can easily find the solution of the voltage across the capacitor. So let's illustrate it with an exercise here. Let me see how long will it take. Okay, I think I will stop here. We have 4 minutes, but I will start solving this exercise inshallah next time, and we'll cover the remaining cases. Then we'll move to the step response, and finally we'll cover the series combination of R, L, and C. So any questions, Shabab?
الله يعطيك العافية دكتور.
الله يعافيك. طيب